Hi students, in the last class we have discussed about the fluid motion, that is Pascal's law, Archimedes principle, law of flotation, viscosity and all. Isn't it? I believe that you all have learned that questions. Today I am going to explain about the types of flow. Here the types of flow may be different ways. It may be steady or unsteady. It may be compressible or incompressible. It may be viscous flow or non-viscous flow. So anyway, I am going to discuss about the two types, steady flow and unsteady flow. That can be more correctly to say that streamlined flow and turbulent flow. Streamlined flow and turbulent flow. So before going to learn this flow, you have to understand one point. Consider a calm flow of water through a river. So when you look at this, the velocity of water at different places will be different. It may be faster at the center, it may be slower near the banks. Okay? But the velocity of the particle at any point is constant. Different places, different velocity. But at a particular point, all the particle crosses with the same velocity. For example, if the velocity of the particle flowing near the bank of the river is 0.5 meter per second, then the succeeding particles flowing through it will have a same value. That is, succeeding particles will follow the previous particle or predecessor. Understand? Succeeding particles will follow the same velocity of the previous particle. So what is meant by streamlined flow? When a liquid flows such that each particle of the liquid passing through a point moves along the same path with the same velocity as its predecessor, then the flow of liquid is said to be streamlined flow. When a liquid flows such that each particle of the liquid passing through a point moves along the same path with the same velocity as its predecessor, then the flow of liquid is said to be streamlined flow. Actually, this can be easily said as an orderly flow. An orderly flow. And we can call the streamlined flow as a steady flow or laminar flow. Steady flow or laminar flow. For example, the water flowing slowly in pipe. When you open the tap, the water slowly, if you open, the water will come smoothly. So that water flowing slowly in pipe is an example of streamlined flow. Understand? Now, the path taken by the particle in this moving fluid is called streamline. The path is known as streamline. If so many bundles of streamlines are there, we can call that as tube of flow. If the bundles of streamlines are there, we can call that as tube of flow. Okay? Look at this figure. Suppose the path is maybe a curve. The streamline may be a curve. Then what is the direction of the velocity of the particle in the moving fluid? It is nothing but the tangent drawn at that point gives the direction of the velocity of the fluid. Understand? If there is a curve-like structure, the direction of velocity is nothing but drawing the tangent at any point. So at this point, this is the tangent. At this point, this is the tangent. At this point, this is the tangent. So tangent to the point gives the direction of the flow of liquid. Also, we note that if any particles in a tube of flow always remains in that tube throughout its motion, isn't it? It will not mix up with the other tube. If there is water flow in one tube, it will not mix up with the other tube. So we can say the axis of the tube is the streamline. When you consider the tube, the axis is the streamline. That is the path taken by the particle. Okay, so streamlines always represents the trajectories of the fluid particles. The next point, the flow of fluid is streamlined up to a certain velocity called critical velocity. How long the fluid will be streamlined? Up to a certain critical velocity. The flow of fluid is streamlined up to a certain velocity called critical velocity. That is denoted as Vc. Or correctly we can say that the steady flow or the laminar flow or the streamlined flow can be achieved below the critical speed. Below the critical speed. Alright. The next type of flow is turbulent flow. This can be called as unsteady flow or disorderliness in the motion of flow. Steady flow means orderly flow. Unsteady flow means disorderliness in the motion of flow. Otherwise, turbulent flow. So, when the speed of the moving fluid exceeds the critical speed Vc, the motion becomes turbulent. What is that? When the speed of the moving fluid exceeds the critical speed, the motion becomes turbulent. Here, the velocity changes in magnitude and direction. Understand? Why the velocity changes? Because the particles does not flow in a streamlined flow. So each particle will not follow the previous particle. For example, air flow behind a moving bus. It is a disorderliness of the flow of fluid. Or the flow of water just behind a boat or a ship. So these are the examples of turbulent flow. Look at this figure. Turbulent flow around the sphere when V equal to Vc. Turbulent flow around the sphere when V is greater than Vc. The velocity is nearly equal to the critical speed. Below the critical speed means it will be very streamlined. So nearly equal to C means some less disorder. And the turbulent flow around the sphere when V is greater than Vc, it is fully collapsed manner. Have you understood? Streamlined flow and turbulent flow. The next topic is Reynolds number. It was explained by Osborne Reynold. Reynolds number. Okay. So Osborne Reynolds explained the nature of the flow of liquid by means of an equation. He developed an equation. It decides whether the type of flow or the nature of the flow is streamlined or turbulent. Let's see what is that equation. That equation is RC is equal to rho VD divided by eta. What is that? RC is equal to rho VD divided by eta. Where RC represents the Reynolds number. It can be noted as K also. It's a number, so we can say it is a dimensionless number. Dimensionless number. It is noted by either RC or K. What is rho? What is V? What is D? Yes. Rho is the density of fluid. Rho denotes the density of fluid. V denotes the velocity of the flowing fluid. And capital D denotes the diameter of the pipe. And eta, in the previous class I explained, eta is known as the coefficient of viscosity. That is, eta is equal to F into dx divided by A into dV. Just recall the coefficient of viscosity from the previous class. So this is about Reynolds number. RC is equal to rho Vd by eta, where RC denotes the Reynolds number, rho is the density of fluid, V is the velocity of the flowing fluid, D is the diameter of the pipe, and eta is the coefficient of viscosity of the fluid. This RC remains the same in any system of units. Okay? Listen. So if the Reynolds number is less than 1000, the flow is said to be streamlined. If the Reynolds number is less than 1000, the flow is said to be streamlined. If the Reynolds number is greater than 2000, the flow is said to be turbulent. If the Reynolds number is greater than 2000, the flow is said to be turbulent. If the Reynolds number is in between 1000 and 2000, the flow is said to be unsteady. In between streamlined and turbulent. So we can call it as unsteady. Understand? So this is the way we can decide the nature of the flowing fluid. So this is about Reynolds number. It is a dimensionless number. Regarding this Reynolds number, you have to understand one more concept called the law of similarity. Law of similarity. What it states? It states that when there are two geometrically similar flows, both are essentially equal to each other as long as they embrace the same Reynolds number. This is known as law of similarity. That means when two liquids, oil and water, of different densities, which flows in pipes of same shapes and same size, there the turbulence is almost the same value of RC. This is known as law of similarity. So if you consider two different densities like oil and water fluids, and both are flows in different pipes, but the pipes have same dimension, same shapes and same size, in that the turbulence sets in almost the same value of RC. That means law of similarity. Once again, it states that when there are two geometrically similar flow, same pipe, same shape, same velocity, geometrically similar flows, both are essentially equal to each other as long as they embrace the same Reynolds number. If the turbulence surges in at almost the same value of RC. This is very important in technological applications. Actually, the space of ships, the shape of ships, submarines, racing cars and airplanes are designed in such a way that their speed can be maximized. Alright, so far we have discussed about streamlined flow and turbulent flow, then Reynolds number. Now, terminal velocity. Terminal velocity. To understand this concept, consider a large liquid column, a container. It consists of liquid, here a small metallic sphere falling freely from rest. Okay, one sphere is falling freely from rest. So this is the sphere. And this liquid is considered as the viscous liquid. Now, what are the forces acting on the sphere? The forces acting on the spheres are, one is gravitational force. Gravitational force acting downwards, that we can consider as W. Okay, gravitational force, which is acting downwards. The next one, an upward force, that we can call it as upthrust force, U, or we can say buoyant force. Okay, upthrust force or buoyant force. Second one is upthrust. The next, this is because of viscous fluid, one viscous force also acting. Viscous force is acts always in the direction opposed to the direction of the motion of the sphere. So the motion of the sphere is acting downward. So what is the direction of the viscous force? It is acting upward. So third one, viscous force. Viscous force. So these are three forces acting on the sphere when it is falling from the rest to the large liquid column. Okay, so gravitational force W is acting downward, Upthrust force U is acting upward and viscous force also acting upwards. Viscous force always acting opposite the direction of the motion of the sphere. Here, at first the acceleration, the downward direction will be higher, isn't it? It is going very fast. So the velocity of the sphere increases and the velocity of the viscous force also increases. So when the sphere falls down, the downward force is actually greater than the upward force. So upward force is less than the downward force. So we can say the velocity of the sphere increases, so velocity of the viscous force also increases. So when the velocity in the downward direction is increases, means the velocity in the upward direction, that is the viscous force, also increases. So at a particular stage, the downward force balances the upward force. Okay, at a particular stage, the downward force balances the upward force and the resultant force on the sphere becomes zero. So we can say it moves with a constant velocity. When the sphere will move with a constant velocity, the net downward force balances the upward force. If the net downward force balances the upward force, what will happen? The resultant force on the sphere becomes zero. So the sphere moves with a constant velocity. That is known as terminal velocity. It is denoted by Vt. Terminal velocity. It is denoted by Vt. So what is meant by terminal velocity? The maximum constant velocity acquired by a body while falling freely through a viscous medium is called the terminal velocity. What is terminal velocity? The maximum constant velocity acquired by a body while falling freely through a viscous medium. Is called terminal velocity. So what is terminal velocity? Once again, the maximum constant velocity acquired by a body while falling freely through a viscous medium is called terminal velocity. They have plotted the graph between time and velocity of the falling sphere. The time is taken along x-axis and the velocity of the falling sphere is taken along y-axis. They have observed the graph like this. What is that? First, the sphere is accelerated initially. So, the velocity increases and in course of time it becomes constant. So, it attains the terminal velocity. So, here it is constant. Understand? Now, we are going to learn the expression for terminal velocity. In order to find the expression for terminal velocity, consider a sphere of radius r. Sphere of radius r which falls freely through the liquid. The liquid is viscous liquid. And eta be the coefficient of viscosity of the liquid. Coefficient of viscosity of the liquid. Here rho be the density of the sphere. Density of the metallic sphere. And sigma denotes the density of the fluid. So consider a sphere falling freely from rest and entering into the liquid column. The liquid is viscous liquid and the sphere of radius r, it has the coefficient of viscosity eta. Rho is the density of the sphere, sigma is the density of the fluid. Of course, we know that there are three forces acting on it. One is the downward force acting, that is gravitational force acting downwards, isn't it? And upward force, upthrust force. Then there is a viscous force which is also acting upward direction. So three forces. What and all? Gravitational force. Gravitational force we can consider as Fg. Then upthrust force, upward force, this is considered as U. Then viscous force, okay, viscous force, that is considered as F. So let's find these values, then we can find out the terminal velocity. First, gravitational force acting on the sphere. What is the formula for force? Mass into acceleration. Here, because of gravitational force, we can say m into g. This again can be written as, this mass can be written as density into volume. Density is equal to mass per volume, or mass is equal to density into volume and into g. Understand? So what is the density of this sphere? That is rho. So rho, volume of the sphere. What is the formula for volume of the sphere? 4 by 3 pi a cube, or here the radius is taken as r, so we can consider as 4 by 3 pi r cube and 1g. So what is the Fg value? Fg value is 4 by 3 pi r cube rho into g. This is actually downward force. Next, the upthrust force, U. Upthrust force is actually equal and opposite to this, isn't it? So this also can be written as mass into acceleration due to gravity. So m into g. So here the mass, m into g means, what is mass? Density into volume. Here the density used as sigma, because upthrust force because of the fluid, isn't it? So we should use the density of the fluid. So what is the density? Sigma, which is acting on this sphere. So 4 by 3 pi r cube into g. So it can be written as 4 by 3 pi r cube sigma into g. The next one, viscous force, that can be written as, actually it is from Stokes' law that we will learn in the next class. So anyway, it is, the formula is 6 pi eta r vt. Now just keep in mind this formula. Next class I will explain this formula. 6 pi constant, eta is the coefficient of viscosity, r is the radius of the sphere, vt is the terminal velocity. Okay. What is the condition for terminal velocity? At a particular stage, the upward force and the downward force balances and moves with the constant velocity, isn't it? So our aim is to calculate terminal velocity. So a terminal velocity Vt, what is the condition? Downward force is equal to the upward force. Downward force is equal to the upward force. So actually what is downward force? Fg. Upward force is U and viscous force. U and viscous force. This again can be written as Fg minus U is equal to what? F. Fg minus U is equal to F. Now substitute the Fg value, U value, F value in this equation and find out the value of the terminal velocity. Understand? Fg 4 by 3 pi r cube rho g, U 4 by 3 pi r cube sigma g, and F 6 pi eta r vt. Rho g minus 4 by 3 pi r cube sigma g is equal to 6 pi eta r vt. So here 4 by 3 pi r cube g is common. We can take it as outside. 4 by 3 pi r cube g into rho minus sigma is equal to 6 pi eta r Vt. So our aim is we calculate the Vt. So Vt alone we can take it as one side. The other things we can simplify. Pi and pi get cancelled. Okay. 1 r cube. Here 1 r get cancelled. So remaining 4 by 3 r square g into rho minus sigma is equal to 6 eta Vt. From this Vt is equal to what? Vt is equal to 4 by 3 r square g into rho minus sigma into 1 by 6 eta. Okay. So we can simplify this 4, 2, 3. So 2 r square rho minus sigma into g divided by 3 3s are 9. 9 into eta. So this is the value of terminal velocity. Understand? Vt is equal to 2 r square rho minus sigma into g divided by 9 eta. From this what can we understand? Vt is directly proportional to r square. Here rho, sigma, density of the sphere, density of the fluid, acceleration due to gravity, coefficient of viscosity of the fluid, everything constant. So Vt directly proportional to r square. That means terminal speed of the sphere is directly proportional to the square of its radius. Understand? So once again listen. Expression for terminal velocity. So there is a liquid column. Here viscous liquid is filled. One sphere is falling from the rest. 3 forces acting. One is gravitational force acting downward, upward force, upthrust force, and viscous force acting upward. Okay. So r is the radius of the sphere, eta is the coefficient of viscosity, rho is the density of the sphere, sigma is the density of the fluid. Now we have to write the 3 forces, that is Fg is equal to mg. Mg means mass equal density into volume into g. So density rho, volume is volume of the sphere 4 by 3 pi r cube into g. 4 by 3 pi r cube sigma rho g. So upthrust force 4 by 3 pi r cube sigma g. Again F, the viscous force 6 pi eta r Vt. So at terminal velocity, what is the condition? Downward force is equal to upward force. So Fg is equal to u plus F or Fg minus u is equal to F. If we substitute all the values, we will get the terminal velocity. That is rho minus sigma. The remaining term we can take it as common outside. Pi get cancelled. R and r cube get cancelled, get r square. So if we simplify this, we will get Vt is equal to 2 r square and rho minus sigma divided by 9 eta, or Vt is proportional to r square. Here, if sigma is greater than rho, this term rho minus sigma become negative. So we can say it has the negative terminal velocity. Okay, negative terminal velocity. If the sigma is greater than rho minus sigma will be negative. So we can say it has a negative terminal velocity. That is why the air bubbles rise up through water or any fluid. This is also the reason for the clouds in the sky to move in the upward direction. Alright friends, today we have discussed about distinguish between streamlined flow and turbulent flow. Next, what is Reynolds number? Give its significance. Define terminal velocity. So 3 short answers we have discussed. Then 1 long answer, that is derive the expression for the terminal velocity of a sphere moving in the viscous fluid using Stokes force. Okay, so 7th question and 14, 15, 16. These short answers we have learned. So these questions done. Thank you, students.